Okay, so once again you are mostly welcome. My name is Mtanda Samir, and now this time around we are dealing with still continuing with our series of Aitel mock examinations, physics specifically here, and now here we are in for item 5. Please, you check in the playlist, we have right there from item 0, we have right here from item 1 up to where we are, item 5. Remember, a physics standard paper has 7 questions, so it means that if we are on item 5, it implies that we have 2 more items to go. And of course, please, as you're watching item 5, just know we have right away from item 1, very interesting, item 2, very interesting, item 3, also interesting, item 4, up right where we are on item 5. Please also remind you that visit our playlist. We have a lot of very many interesting things. It's better you visit there and you enjoy. Of course, the aim of this channel is at least to have the results a bit change as far as science is concerned. That's why, please, as teacher Mtanda, okay, we don't necessarily charge people money or monthly charges and so on. We don't do that. We don't do that really, because our aim here is to at least demystify the new curriculum by trying to at least break down some of the items. Okay, so in here we are in for item 5, Wakisha revision question, physics paper. We are doing a full paper, in fact, so we get it covered. But we have, anyway, let's proceed. Okay, we now simply remind you to subscribe to the channel, please. There's only the token of appreciation you can give to us right here. The only way we can show that you are really impressed with the work we are doing here is by subscribing. Of course, the more the subscribers, the more we also get agitated a little bit and we get into the thing, too much vibe, and we keep it going. Okay, so your subscription is highly called for, please. It's highly called for. All right, now with this, without wasting time, I think let's get there and we look into the question. Okay, so there we are looking at item 5, Wakisha specifically, and without wasting time, let's get there. All right, good. Let's go slowly to the saying. Conrad is required to prepare a bath for his young brother Alex. According to the advice got from his mother, the bath should be between 40 degrees Celsius and 42 degrees Celsius. Yeah, by the way, when you're going to bathe, you realize that, of course, I know you all know what this really means, like to bathe some warm water, but you can't really tell in terms of figures which temperature must we really use right here. Okay, a bath must be between 40 and 42 degrees. That's some water enough to be bathed, which some people call hot water anyway. So we say Conrad, however, has 2 liters of hot water at 100 degrees Celsius and 6 liters of cold water at 20 degrees Celsius. Now, please, if you look at this item, you need to also watch item 4 too. After this, in fact, you watch item 4 also. Or if you have just started, you can go and watch item 4 first before you come to this, such that you can really understand this better. Okay, all that Conrad has to do is mixing in an aluminium pan of mass 3.5 kilograms and specific capacity 660 joule per Kelvin per kilogram per Kelvin. As a learner of physics, help Conrad to establish and inform his mother whether the water is warm enough for Alex to bathe. Remember, the warmth is between 40 and 42 degrees. We should look into that. Okay, if it goes beyond that, it's very hot. If it goes below that, it's very cold. It is not warm enough. So in what ways would you prevent the water from cooling very fast? Okay, help Conrad to understand why water is used as a coolant in engines. Let's go and get that answered. First of all, we help Conrad inform his mother whether the water is warm enough. Now what you're going to do is we're going to pick out some of the things here. Okay, so this is our question already, and I've asked us a question. So you realize that we have the 6 liters of hot water. They are at what temperature? 100 degrees Celsius. We shall get that in drawn for us. Then 6 liters of cold water. Okay, 6 liters of cold water at 20 degrees Celsius. Cold water at 20 degrees Celsius. Have it right there. Okay, so we have 6 liters of cold water in simple terms. Now, are you saying this time around again, the volume, instead of mass, they have given us the volume. Remember, volume can be measured in centimeters cubed, volume can be measured in meters cubed, and volume can be given in liters. Be reminded, please. So whenever you're dealing with heat questions and you have liters given to you, just know you can use those liters there, since it is a volume, to get the mass, since we know that mass is equal to the density times volume. And if you're dealing with water, density of water is always 1000 kilograms per meters cubed, right there. So that's what we're going to use. That's what we're going to use. Let's, I think, get there and you see the way forward. So now, but of course they will tell you that where necessary we use this. Density of water is 1000. I talked about that, kilogram per meters cubed. Specific capacity of water is 4200, and acceleration due to gravity is 10 meters per second squared. Now let me put something just to confuse you around. Now this one here, acceleration due to gravity, may not necessarily be important here, but I only put it for you to get confused and maybe accidentally use it. Okay, so with that, let's go and get there. So we're getting our tin is done. Remember, we're mixing the water for Alex and it's Conrad mixing. So we have our tin there. This tin is having cold water, cold, and now we are mixing it with the hot water. If you can really see that, hot water. Now you must get the labelings ready here. You must get the labelings ready here. So this one here is cold and it's at 20 degrees. Okay, I hope you will understand by the figures themselves. So we have this water at 20 degrees, and now we are mixing that water and pouring it in here. And after pouring, this is the basin of ours which Conrad will use to bathe. But remember, this can we are pouring is an aluminium pan. We are pouring it in an aluminium pan. Not must you know is that. Now here we have, look, we have a lot of things. We have cold water, if you can really see that. We have, okay, aluminium pan, have aluminium pan. Please still also we have, okay, hot water. Now you must know, let's get to know here which ones will gain heat and which one will lose heat. First of all, let's see. Think about cold water. Will it gain heat or lose heat? I'll use G. It will gain heat. Okay, aluminium. What will it do? Aluminium pan, a saucepan. If you pour the hot water, does it gain heat or loses? It will gain. It will become more hot. What about the hot water itself? It will lose heat. Now, what does it mean? From, we know the acronym that heat lost is equal to heat gained. If you can really see that, is equal to heat gained. And now what does that mean? Heat lost, we have what? We have only hot water. Therefore, we shall say the mass of hot water, specific capacity of water, times the temperature changes right there. That will be theta 3 minus theta 2. Just like we did, if you can really check in, anyway. So this one is equal to, if you check on item 4, has a resemblance of this. Now, here heat gained, we have two guys. We have the one for cold water and aluminium. So we shall say mass of, okay, cold water times specific capacity of water as usual. Temperature changes will be theta 2 minus theta 1. Okay, plus, since we have two of them, so we add, plus another heat gain is the one for aluminium. So mass of aluminium, allow me to use capital F aluminium, specific capacity of aluminium, and temperature change. Now temperature change for this side will always be the same. Temperature change for heat gain is always the same, theta 2 minus theta 1. So theta 2 minus theta 1. And that's how we shall get that done. And I think without wasting time, let's, I think, get there. Okay, good. So with this, let's get there. Okay, so we are starting, we say heat lost by hot water at, now, no, sorry, this one is hot water at 100 degrees Celsius. Hot water at 100 degrees Celsius is equal to heat lost, sorry, this is meant to be heat gained. Sorry, don't know why this error just came up again here. This is same as heat gained, if you can really see that. Heat lost must be equal to heat gained by cold water, and this is meant to be and, not at, but and aluminium pan. So let's see how this can get, how we can get this done. Okay, now we have from the formula that mass of hot water times specific capacity of hot water is equal to theta 3 minus theta 1. Why? Remember this one is at 100, but the final temperature where we are going, the arrow is theta. So it means that what you will do, you look at this. Remember where we are going. It means that this one here the 100 is contributing to the theta 2. So you compare that which one is bigger. So you see that it will be 100 minus theta 2, but of course 100 is theta 3. So that's why you have theta 3 minus theta 2. Hope that really makes some sense. I will erase of that and still have this explained. Now, even this 20 also brings about the effect on this theta 2. But compare between the 20 and the warm water, which one is higher? It is theta 2. So you will say theta 2 minus theta 1. That's why here, like this, we have that. Okay, we have theta 2 minus theta 1 plus, okay, the mass of aluminium. Okay, this is meant to be aluminium still. Allow me change this. Please, this is meant to be aluminium. It is some typing error here. Please, even this one is meant to be gain. Or is that typing error? I'm really sorry for that. Now, theta 2 minus. Now, the temperatures for this side, after the equal sign, once you're adding any two things, the temperatures must be the same. You see theta 2 minus theta 1, theta 2 minus theta 1. Let's do the substitutions. But again, what do you want to see here? What do you want to get? We want to get theta 2. That, after mixing these two, remember here, to explain the diagram, when we mix the cold water into hot water, we get some water of a certain warmth, which temperature we don't know. But this water is in a pan of a certain mass, say MA, and specific capacity CW. So let's go and see that. Remember, we have this in terms of the masses. Now let's summarize for you the masses. Like, say, for example, the volume of hot water was 2 liters. Now I told you that whenever I have liters here, you can just get those 2 liters, divide by 1000, you show the working times 1000. And how you do that? Remember, the liters, you must convert them. Remember, it was a volume, you must convert it into mass. This 1000 we are dividing, we are multiplying with, is the density of water. Now why are you dividing by 1000 is converting from liters to centimeters cubed. So you have it at once, 2 over, you get the liters given to you. Of course, it's a volume and you want it into mass. So you get the liters given to you, divide by 1000 times 1000. Of course, it will cancel. And then you remain with the 2 kilograms, and that will give you a mass. Let's have that done right here. So this will be, now volume of this was 2 liters. Also, let's get this done. I've explained the mass will be equal to 2 over 1000 times 1000, which shall have 2 kg. Are you seeing? So in that mass of hot water will be 2 kg. Let's do the same here. Mass of cold water will be, do the same. Mass of cold water will be 6 over 1000 times 1000, which will give us 6 kg. So mass of cold water, we have it as that. Then not forgetting in the question, go back and check in the question, mass of aluminium is 3.5 kilograms given to us already in the question. Please, a simple reminder, maybe someone has just doing the video, this is not lost but is gain. This is not at but is and the and is the plus we have right there. And it's not at it is not at 80 degrees but at 100. 8 is not there, so it is at 100. I hope you really come to have that changed. So we have the masses. Now this one will be right here, this one mass will be for this mass will be for this. And remember, we have theta 3, we don't have theta 2, because theta 2 is the one we are looking for around this area. After mixing the whole water, what will be the temperature there? We shall compare with the mother, which the mother's temperature, which he wants the Alex to bathe, is between 40 to 42 degrees. So let's calculate the theta 2. We'll compare with the answer for Alex Conrad's mother. So let's get there. With this, we shall get to see that substitute. Now remember, the specific capacity of water is 4200, and we have it right there in the first context. We have that. Now minus theta 2, so we shall have that equals to 6 times 4, 2000. Okay, still again there, so plus, okay, 3.5. The specific capacity for copper, aluminium is 660, like that. Now next, what we're going to do, we're going to expand simply, and the expansion will be done as that. So 2 times 4 will give us 84, okay, 840,000. 2 times 4 times 100 will give us 840,000. Now the answer here again, times theta 2, you'll get this. Okay, this is equal to, you see that when 6 times this, you shall get that, and the 6 times 4200 times 20 will give us that, plus, again you see that a 3.5 times this times that will give us this, will give us, okay, will give us this. Then 3.5 times 660 and 20 will give us this. Now next, what we're going to have, we're going to simply press in our calculator, and maybe first of all correct like terms. These ones with theta 2, it must go the other side. Meanwhile, these other values must come over this side. Even this one must come over this side, of which they will come positive. So it will be 84,000. When this one comes over, you can really see that. Now you see here, we are getting this side and it's crossing the equal sign, so it becomes a positive. We are getting this side, it's crossing the equal sign, it becomes a positive. Then this side we shall maintain this, as we have there, plus this, then plus also it is a negative, crossing the equal sign, it becomes a plus right there. Now, since you have them like that, you can now use a calculator to have them added. So when you add this plus this plus this, you get that using calculator. So equals to, when you add this in terms of theta plus this in terms of theta plus this in terms of theta, you get that. Now remember, you want to get the value of theta. So what are you going to have? Dividing both sides by, okay, a 359, or rather a 35,910 theta 2. Divide on both sides, it will cancel, shall remain with our theta 2, which will be equal to, divide here, what are you going to have? So realize that what you're going to have here finally will be, in simple terms, will be that. So theta 2 is equal to 38.71 degrees Celsius. 38. Now the question remains, remember the amount that I said, between 40 to 42 degrees Celsius, a temperature good for bathing. Now we really see that the 38 is below. Therefore the water is not warm enough. So shall we say the water will not be warm enough for bathing. Yeah, 38 point. Now the temperature of 38.71 degrees, you can just try to touch your body. The body temperature you have is the one which is as hot as that temperature you're seeing, and of course that can't be enough for bathing. In a way, it can't be that effective as far as bathing is concerned. And now that marks the end of where which kind of mixture should do. Will it work out if Conrad mixes in that way? Not really. The water will not be warm enough for bathing. Alright, good. Now with that, let's go and get this part answered. There's a part which asked for, let's get this. Now there's a part which was asking for why water, ways how we can prevent the water from cooling. Now you're saying that water can be prevented from cooling in the following ways. Please, you go in the question, we have that part saying how can you prevent the water from cooling. So you can prevent the water from cooling in the different ways. Among them is what we have right here. Now, by simply you can by covering hot water using a lid. Yes, you all know that when you have a saucepan and you boil your water, you come and cover this water here using a what? A lid, so that the water doesn't become warm or not allow in air to go and make it cool down. So using vacuum insulated containers. So vacuum insulated containers are more like this, whereby like this, even the cover itself is vacuum insulated. Vacuum is a place without air. So this one here is a vacuum, this one here is a vacuum, this one is a vacuum. It means that if you have something hot inside here, if heat comes, it only ends on these walls. This area here is a vacuum, it has no air, it cannot conduct heat, or it cannot allow heat losses. So that's why we use vacuum insulated containers, using hot water bottles and flasks. Of course, you all know those portable water bottles which can keep water hot for a long period of time. You can use that. So using electric heating pads or warmer, yeah, you can have a warmer. Then you, of course, that warmer has a meter somewhere whereby you have to regulate which kind of temperature you want. You can even just enter it. Maybe you want 42 degrees, then the water will boil to that, you get it for bathing. Then also using a thermal mass. Now thermal mass, these are wooden or concrete, okay, heavy bodies made to prevent heat loss. They are especially put in buildings. They especially put in buildings to prevent heat loss. Those using thermal mass. Thermal mass is, it can be made out of wood. In fact, wood put in the house to prevent heat losses. But those ones are specifically used in winter seasons in some European countries like there. So you realize they can even use the heavy concrete whereby any little heat they have inside the room cannot be lost. We call that thermal mass. When you join very many materials together to avoid, or thermal mass can just be a very thick wall. A very thick wall can act as a thermal mass. Maybe where you're watching this video from, you can just look around. If the wall is very thick, then it can act as what you call a thermal mass in simple terms. Then also, they asked us that, why do you think water is used as a coolant in most of the engines? So we get that answered. So water is used as a coolant because water has a high specific heat capacity. meaning that when you have water in the, I'm explaining this high specific heat capacity, when you have water in the can, like there, then you start boiling it. When you start heating it, the water, when you start heating, when you start heating the water, when you start to heat the water, now what does it mean? When you start heating the water, this water can't just disappear. It can't just disappear, of course, you all know that. The water will take some time to boil. The water will take some time to boil. Now that time this water takes to become hot, that time the water it takes to become hot is what we call specific heat capacity. That the water maybe, in order for water to become hot, the amount of heat we need is 4,200 joules per kilogram per Kelvin. That every 1 kilogram mass of water requires 4,200 joules of heat energy for it to become hot. We call that specific heat capacity. Next, it has a high thermal conductivity. Now, thermal conductivity is a rate at which a substance conducts heat. Now, water is a very good conductor. I find that any little heat added to water can easily be felt. Like an example, try to put a saucepan containing water onto a heating source. Even just seconds, if this is water in the saucepan, if you enter your finger in here, you can feel the warmth, meaning that the water has a high conductivity. The next, water, it has a low viscosity. Now, I'll explain the viscosity using porridge. Now, you all know what porridge is versus the water. Now, I want to ask, of the two, which one is easier to drink? It is water. Now, why is porridge hard to drink? It's because porridge is viscous, or it has a high viscosity, meaning that porridge is sticky. In simple terms, is sticky. However, water is not sticky, it doesn't stick onto the walls. Okay. The next, it is non-toxic and non-flammable. Yeah, water cannot easily catch fire, and water is not that poisonous. That works. So, the next, resistant to corrosion and chemical reaction. Yeah, water doesn't respond to all chemical reactions. That's why I find that where the coolant of the engine in the bonnet is in the front, and even some batteries are there. So, water doesn't allow in some chemical reaction. Then also, water is very cheap, low cost, and also ever available. Water is cheap and also ever available. Please, before we complete this video, I want us to go and make some clarifications here. You know, some people, they might have joined this video and they don't know what's going on here. Please, here it is meant to be 100 degrees Celsius, not 80. That is not that. The next, here it is meant to be heat gained by cold water. Then this one is meant to be earned. Those are the changes you have right there. Then everything will just be as usual. Okay, and with that, I think we are ending here. I would simply say thank you for watching. May God bless you. Let's get there. We end this.